So I'm a postdoc at Leiden Observatory, and I would like to thank the organizer for giving me the opportunity to present the work that I've done for my first year of postdoc, and of course all of you to still being here. So I'm going to talk about sulphur-bearing species towards NGC 253. So first I will introduce the source. So NGC 253 is a prototypical starburst galaxy. It's a nearby starburst galaxy from the extragalactic point of view, at least. It is, so you have the image here. It has a nice inclination, which allows us to really separate the disk of the galaxy from the large-scale starburst-driven outflow. And this source is pretty much, it has been studied a lot, in particular its central molecular zone, or CMZ, I'm going to say that after, which has been classified as a starburst nucleus because half of the star-forming rate of the total galaxy actually happens there. And within this central molecular zone, there are 10 giant molecular cloud, or GMCs, that have been identified and well studied. These are the gray blobs all over the CMZ. And in the follow-up, I will make a distinction between the GMCs that are located in the outermost part of the galaxy. So I will mention the outer CMZ and those who are detected in the inner CMZ. And because this galaxy is pretty well known, and because of its CMZ that is pure starburst, so the nucleus, there is no active galactic nucleus, the black hole is not active. That's been the target of the Alchemy large program. So it's a HALMA, comprehensive high-resolution extragalactic molecular inventory, which is a full survey made with ALMA from bond 3 to 7. With a pretty nice spatial resolution because we can resolve the giant molecular cloud in this galaxy. So there have been 15 published papers of alchemy so far. They are all on arXiv. So if you're interested, you can check them out, and more are going to come. So we are interested in sulphur-bearing species, and previously to alchemy, there have been a few studies of sulfur in other starburst galaxies, but there was no really clear consensus about what they are tracing there. So different studies studying the same object would come to different conclusions. For example, H2S would, for example, be said as a tracer of a hot core-like region, so it is thermally evaporated from the grain, while another study would conclude it as a shock tracer. And the thing is that all of these studies were limited by either a low angular resolution because they were made with single dish telescopes, or they had only a few number of transitions, which of course can really affect the kind of analysis that you can do. But thanks to alchemy, as I mentioned, we both have a high enough angular resolution and a high number of transitions to really perform a complete investigation for the most common sulphur-bearing species towards the starburst nucleus. This is what we wanted to do. So here are the 7 sulphur-bearing species that we looked at, and we just wanted to know what they are tracing in that galaxy. So we first look at the emission distribution of the species, and we notice some differences. So here you have the integrated intensity map of the lowest energy level transitions of each of the species that we looked at. And in the first panel, just the magenta circles are all the 10 positions that we looked at. But already we can see that, for example, we have the species that are the most extended ones. So H2S, CS, and SO, they are detected throughout the CMZ and have their peak of intensity towards the innermost GMCs. On the other hand, OCS and H2CS are much less extended, and we call them GMC-peaked species because you can see that their emission is really concentrated towards each of the giant molecular cloud, and they have a lack of emission that is towards what we think is where is the black hole. Finally, CCS and SO2 were the species that was mostly detected towards the inner GMCs. There is a really poor detection in the outer CMZ, but this could be, of course, a sensitivity issue. And because we had a really large number of transitions, then we could really constrain the physical parameters. So we did 2 methods, an LT and non-LT. I'm just showing you here the non-LT results. So you have the density temperature 1 sigma solution for some of the sulphur-bearing species towards 2 GMC located in the outer part of the CMZ. And what we can see is that in all the 5 outermost GMCs, there is the same pattern in every GMC. So you have SO that is tracing the most warm gas, while a CS is tracing the most densest. And CS here has 2 components because we could not fit all the transition as a 1 gas component. We have to model 2 gas components in the model. We also compared with previous alchemy studies. So we compared with HNCO, which is a well-known low-velocity shock tracers in that galaxy, and density temperature conditions traced by the ratio HCN over HNC in the outer parts. And in the outer CMZ, what we found is that SO is always well correlated with the gas traced by HCN and HNC. In the inner CMZ, it's a bit more a mess because all of the sulfur-bearing species need 2 gas components at least, so usually 1 colder, 1 warmer. And each of the inner GMCs has a very particular distribution. They are not all the same like in the outer one. And so you can see, for example, SSC2, where most of the species have a really lower temperature compared to GMC6, so less than 60 Kelvin for most of them. H2S was, however, always tracing the most dense gas. And in the inner part of the CMZ, we could also compare with previous studies that derive physical condition for CCH and that of SO over H3O+. But all of these are well-known GMC tracers and are known to be sensitive to cosmic rays. But what we could see by comparing with previous alchemy studies is that OCS, H2S, and the high-level transition of SO were more or less always well correlated with HNCO. So it seems that we have really some sulfur-bearing species that are tracing maybe shocks and others that are tracing giant molecular cloud. So we wanted to take a step further and compare with well-known star-forming regions in our galaxy. Of course, we are not looking at the same scale, so we just compared abundance, relative abundance ratio. So you have here the ratios for several different sulfur-bearing ratios as a function of different environments. We have the 10 regions in NGC 253. We compared with 2 well-known outflows and shock regions, hot cores, high UV PDR, so Orion Bar and Monoceros R2. The low UV PDR, such as Orsed, Nebula, was really giving relative ratios that were lower, so it was not matching at all our results. And then some different clouds, so prototypical dark clouds and a galactic center cloud, which is GC. And there are some abundance ratios that are similar to what we found in some of the galactic star-forming regions. For example, if we look on average, the abundance ratio OCS over SO, both the lowest energy transitions, they are relatively similar to hot cores or galactic center cloud. On the other hand, if we look at the ratio H2S over the high transition of SO, so this is the orange one, it is very similar to the outflow and shocks regions and hot core regions. So on the one hand, we had the gas physical parameter derived for each of the sulfur-bearing species, maybe a similarity with previous known alchemy tracers, and this comparison with galactic environments. And we tried to come up with a kind of a scenario about what sulfur-bearing species are tracing. So this is just a scheme to show you what we discuss in the paper. I'm going to go very fast because I don't have a lot of time, but we have a lot of discussion in the paper. So these are just the representation of 1 GMC in the outer CMZ and 1 GMC in the inner CMZ. We represented the ongoing star formation with 1 protostar and outflow, but just multiply that by a lot for extragalactic GMC. And what we propose is that there are some sulfur-bearing species, such as H2S, the low transition level of OCS and H2CS, and the high one of SO that are shock tracers. And we discuss more in the paper if it's a Franck shock tracer, post-shock tracers, and so on. SCS and SO, the low transition level, are tracing quiescent dense gas. And there are some component of sulfur-bearing species or sulfur-bearing species for which we could not constrain. So for example, SO2 and the high AU transition of H2CS and OCS could be both explained by shocks or hot core-like regions. And for the high EU of CS and CCS could be explained by either a shock region or a dense gas region, GMC region. So This is where we stopped in the paper. We wanted to keep it observational, but now we want to compare with chemical modeling, of course, to try to see if we can confirm our scenario, constrain what we could not constrain observationally, and try to see if we can characterize a bit more the type of shock that are occurring in NGC253. So this is an ongoing work, and I started by collaborating mainly with Kasia Dudkowska and Serena Viti on that. So we are using the UCL Chem time-dependent gas grade chemical code. It's an open source code. And we tested two models, the hot core model and the C-shock model. And of course, in the models, we looked at the pre-warm-up phase in order to try to have a model of a quiescent dense gas, the hot core phase. And for the shock, we looked at the really shock phase and the post-shock phase to have the different kind of chemistry. So we used a grid that was made for another project that is supposed to look at the center of our galaxy. So the grid is not really, was not made for NGC253, but I will come back on that later. You have the main parameter that we use, that were used in the grid, but because there are some parameters that we know well for NGC253, we looked at the models. We didn't look at all the models. So for example, the cosmic ray ionization rate in NGC253 is pretty high. It's at least a factor 1000 compared to the galactic one. So we just compared the models with this high cosmic ray ionization rate with our observation. And although the hot core final temperature goes up to 500 Kelvin, we just stopped the models we looked only at the models that goes up to 300 Kelvin because this is the gas temperature, maximum gas temperature found towards NGC253 with also other previous studies. Yeah. So I will show you two main examples. The first one is H2S over OCS. In the paper, we mentioned that the ratio in these two species were tracing shocks. So we wanted to compare with the chemical code. So you have the ratio as a function of the final temperature of the hot core that has been modeled for different initial density. And overall, you can see that statistically, we cannot reproduce the observed value for one of the regions towards NGC253. And I forgot to mention that each color is the measured value towards the position in NGC253. So it does not, I mean, the model can reproduce the observations, but only mostly in two regions. We wanted to also understand if it makes sense to look only at the ratio. We also compared the individual abundances of the species. And you can see that while the hot core model can reproduce the observed abundance of H2CS, it cannot reproduce those for H2S unless it's a temperature of 50 Kelvin, which is way too low for what we observed. So the hot core model does not seem to be suitable. If we look at the shock model, the C-shock model, this time, statistically, up to 20 kilometers per second, the models can really retrieve all the measured value throughout the different GMCs in NGC253. And again, if we look at individual abundances, this time H2S abundances can be reproduced by the model, and this for every velocity. So looks like in this case, the shock scenario is indeed favored for velocity up to 20 kilometers per second. Another example is where we could not constrain observationally. But for example, the ratio OCS over SO2 could have been explained both by shocks or hot cores. And if we look at the hot core model and the individual abundance, actually, the hot core model can be suitable only if we have a 200 Kelvin gas or 300 Kelvin gas, and for a density larger than 10 to the 7th particle per cube centimeter. And this goes, this is relevant to the observations. We didn't have the information about the density, but it goes well with the observation. So the hot core scenario works. But the shock scenario also works, as you can see. So we cannot see well here, but trust me, it represents all the abundances. And if we look at the observed ratio, statistically, it's reproduced by the model. But you can see that most of the model actually are out of the observed value, and we would need to go into much more detail to see exactly which model are reproducing the observation and which are not. But overall, the shock scenario is also suitable. We cannot distinguish again. But as I mentioned, the grid that we are using has been made for the galactic center of our galaxy, not for NGC 253. So we are currently running a new grid, and we changed a couple of things. First, we changed the final mass of the object that is modeled. Initially, it was 10 solar mass, and we will use the most intense mass possible for UCLChem, which is 60 solar mass, because NGC 253 has a much more intense star formation rate than our galaxy. So we want to see how it affects the sulfur-bearing abundances. And in the code that we are using, there is actually currently no sulfur depletion, but as Angel already told you before, there is a depletion of sulfur in the densest gas of the phase, and this is clearly what we are tracing here with sulfur-bearing species. So we will introduce a factor of 10 just to see how it affects the sulfur-bearing species. We also refined a bit the grid to make it also faster, and we will, in particular, increase the shock velocity that is modeled. But because from the literature, the magnetic field does not seem to be that high in NGC 253, we will also try to model G-type shock. So this is really still work in progress. So stay tuned for more, and thank you for your attention.